Hello again. Today we're going to do both the confidence interval and conduct a hypothesis test for testing two means with independent samples. And more specifically, we're going to be looking at the cases where sigma is unknown. Last time we looked at independent versus dependent, we were looking at independent versus dependent events. And this is clear back in chapter 4 when we were looking at probabilities. Two events were independent when one event occurred. It did not affect the probability of the other event to occur. Now, in this case, we're looking at independent samples. And this is basically where if one sample has values and that sample having those values does not affect the values of the other sample. So sometimes people may say that these two samples are in no way naturally paired. So oftentimes you'll see that independent samples will have different sample sizes. This isn't necessarily guaranteed, but this is often the case for independent samples. Now, if they are in fact dependent samples, that basically means that they have something in common or that they're matched or paired in some way. And this can or can, or so some examples where they are naturally paired is if you look at before versus after treatment has been applied. So the idea is that you use the same patient in both samples. So you measure something about the patient or subject before you do the treatment, and then you measure them after they do the treatment. You can also look at husband and wife. So, for example, you might look at the weights of husbands and wives. Could be that they eat the same types of foods. They may be their weights may be dependent on something that they have in common. You can look at adjacent plots of land if you're trying to grow good quality wheat, and you may be comparing different types of fertilizer used for both types of wheat. They do have the same types of soil. They have the same types of rainfall applied to them, or maybe the same type of irrigation. So again, they have a lot of similarities. So because of this, we treat them as dependent. Now, dependent will be covered in the next section. So for now, we are only looking at cases that are in fact independent. The problems will not necessarily state that they are in fact independent. So you may have to read a little bit into the context of the problem, as well as looking at your sample statistics to figure out whether or not these are in fact independent. So assuming that sigma 1 and sigma 2 are unknown, we basically will have to use S1 and S2 to estimate our population standard deviations. Now, there's two ways we can effectively estimate this. And this basically just depends on whether or not we can assume that the variances should be the same between both populations, or if they are not the same. Now, for this class, we will basically just have to be told whether or not these two population variances are the same or if they are in fact different. So they'll either say that, assume that the variations are, so it'll say that the standard deviations are different, or it may say to pool them or not to pool them. So whatever case, it will have to specify it. For outside this class, I've seen this in other textbooks where you basically just divide S1 over S2 and you figure out if one of these numbers is at least twice the size of the other. So you may have it be between 1/2 and 2. So if when you divide these, you end up with a number between 1/2 and 2, or in other words, one of the numbers is not twice as large as the other, this basically means that we would pool them. But again, this is not what we're going to use for this class. So again, this is something I got from another textbook. This is not something we're going to use in this class, but it is something that may help you in the future. So if we want to pool the standard deviations together, we need some way of pooling them, and we would actually use this formula. Now I have to kind of briefly mention this because it looks a little funny. This S12, this basically means we're taking the standard deviation from the first sample and we're squaring it. And that same thing for S2 squared. Now, why does it make sense to pool them? When it says that they are in fact pooled, or the standard deviations are similar? Well, we're basically trying to get a better estimate of what sigma 1 and sigma 2 are. So if sigma 1 equals sigma 2, we need some way of getting a better estimate of what those are. Since we have two samples, we can just average those S1 and S2 together. So that's actually what this formula is doing, is it's averaging them based off of their sample sizes. So our assumptions for this hypothesis test, as well as the confidence interval, is that we have simple random samples, they are independent samples, and we have to have the central limit theorem for each sample or population. So our null hypothesis, we assume that the means are the same. The alternative is that they are somehow different, whether mu1 is less than mu2, mu1 greater than mu2, or that mu1 does not equal mu2. To continue this, we have the two cases where sigma 1 does not equal sigma 2, so this means that they are not pooled, or where sigma 1 equals sigma 2, which is where they are pooled. Another thing to note, because of our null hypothesis assumption, we can assume that mu1 minus mu2 equals 0. And you'll notice that the main differences between the formulas are, of course, where we use SP or if we use S1 and S2. Now, something that you're really probably not going to like is that the formula for the degrees of freedom is extremely complicated for the not pooled case. And this is where you end up actually getting decimal numbers if you do this using my Excel spreadsheet that I made, or if you do this on the calculator. Now, of course, this is not a very practical formula, especially if you're doing this by hand. So a much simpler version is if you were to do this by hand, you would take the smaller of n1 minus 1 and n2 minus 1. And this, of course, will still give you a different result entirely. I would personally recommend just sticking with the degrees of freedom that Excel spits out for you. Okay, so of course, because we are testing two population means, we'll be using the two sample t-test on the calculator or on Excel, and we'll actually also use the two sample t interval on Excel as well. In the pooled case, the degrees of freedom is a lot nicer. It's just n1 plus n2 minus 2. But using this means you'd have to calculate the pooled standard deviation first, which means that this formula for the test statistic ends up being a lot uglier than you would expect it to be. Confidence intervals use the same degrees of freedoms as the previous slide, and similarly we use SP instead of S1 and S2 if they are pooled. Otherwise, we just use S1 and S2. So for this example and the next example, we're going to do both a hypothesis test and a confidence interval for this example. So listed below are student course evaluation scores for courses taught by both female and male professors. So we're going to use a 0.05 significance level to test the claim that the two samples are from populations with the same mean. Does it appear to be a difference in evaluation scores of courses taught by female professors and male professors? We're going to assume that the standard deviations are in fact different, meaning that these are not pooled. So the null hypothesis, we will assume that mu1 equals mu2. And we're basically looking to see whether or not there is in fact a difference. So that would suggest that is our alternative hypothesis, that mu1 is not equal to mu2. So before looking at the Excel spreadsheet, notice that 1 is going to be represented by females, or female professors, and 2 is going to be the male professors. So now looking at the spreadsheet, I went ahead and typed in the values, and we get our test statistic to be negative 0.6599, and our p-value be 0.5172. Now I forgot to write down alpha, but our alpha is 0.05, so this is definitely larger than alpha, so we would fail to reject the null hypothesis. When we do the critical value approach, notice that our degrees of freedom is 19.0634. So if we do this using the table, since our degrees of freedom is close to 19, we actually have two different critical values because our alternative hypothesis is a two-tailed test. Since our significance level was 0.05, that means our area in both tails is 0.05. So that means I'm looking at this value at the area in two tails. Now, of course, you may be used to just find the area in one tail, which is fine. In which case you would divide alpha into two parts, which is 0.025, and you'd be looking at the area in one tail. Either way, we are looking at the middle column. Looking at the middle column, we get our critical value of 2.093. Because this is a two-tailed test, we have two critical values. So we have negative 2.903 and positive 2.903. Our test statistic, again, was negative 0.66. So this is probably around here. And because, again, this is not inside our rejection region, we would fail to reject the null hypothesis in favor of the alternative. We failed to support the claim that a difference exists in student course evaluations for female and male professors. So what if we were to create a confidence interval for this? Now, notice that it actually does specify what the confidence interval is, so we don't have to go through the math of trying to figure it out. However, because the last one was a two-tailed test, we already knew that the combined area of both tails was 5%, meaning that the middle area had to be 95%. So this had to be a 95% confidence interval. Also notice that I formatted this sheet a little bit different from the 2-prob z interval and test sheet. And how I formatted this is I basically went ahead and made it so that if you typed in the sample data here, you did not have to retype it in for the hypothesis test and then type it in again for the confidence interval. All you have to do is just state what the confidence level is, and down here it spits out the confidence interval. So this confidence interval is basically telling us that the main difference between mu1 and mu2 is somewhere between negative 0.52 and 0.275. Now, because you might be used to doing the proportions from the previous section, these are in fact not proportions. These are evaluation scores, which I'm guessing are somewhere between 0 and 5, 0 being poor to 5 being excellent. So the differences we're saying are somewhere between 0.528 points and 0.275 points. Now, because we're between a negative and a positive number, that basically means that mu1 minus mu2 can in fact equal 0, or in other words, 0 is inside our confidence interval, which means that mu1 can in fact equal mu2, meaning there is in fact no difference. We are 95% confident the true difference in student evaluation scores between female and male professors is between negative 0.5283 points and 0.275 points. In this last example, we're going to compare how creative people can be depending on the color of the background. In this case, we have our two samples, one for the red background and two for the blue background. And we're going to assume that these are normal populations and that each sample is a simple random sample and that sigma 1 does not equal sigma 2. Notice that the claim is that blue is supposed to enhance performance on a creative task. Since blue is 2, this is basically saying that P1 will actually be less than P2. So the null hypothesis is that P1 equals P2. The alternative is that P1 is in fact less than P2. So this is a left-tailed test. Significance level is 0.01. And using Excel, we will get the test statistic as well as the p-value. Treating 1 as the red background and 2 as the blue background, plug the values into the input, selected no for the pooled, and our hypothesis test is that this will be less than mu2. Scrolling down here, I can see that we do have our test statistic as well as our p-value. Our test statistic ends up being negative 2.979 rounded, and our p-value is 0.0021. So our degrees of freedom, according to Excel spreadsheet, is 58.11153827. Now notice in this case that we do not actually have 58. So if we were to use the table, we'll just have to assume that degrees of freedom is 60, which is going to be the closest number that we have to 58. Our significance level was 0.01. So that is the area in the left tail. So that's the area in one tail. So we'll be using the second column of these tail values. So that tells me that my critical value is negative 2.39, since that is in our left tail. Now keep in mind this is a left tail test, so our test statistic is to the left of our critical value, and our p-value is less than alpha. So we reject the null hypothesis in favor of the alternative. And in fact, we have sufficient evidence to support the claim. Now, of course, I don't really have a ton of room, so I just left the claim as the blue enhances performance on a creative task. So for this example, when we're looking at the confidence interval, we have to first make sure that we know what confidence interval we're looking at. So since that last one was a left tail test, that meant that the area in that left tail was our alpha, which was 0.01. Well, the area in the right tail must also be 0.01 since we're treating confidence intervals as two tails. So that means we want 0.98 in the middle. So this is a 98% confidence interval. From the last example, I already had the values typed into our input, already have no selected. It doesn't really matter what the hypothesis test is here, because all we're really looking at is our confidence level and our confidence interval output. So my confidence level is 0.98 since it's a 98% confidence interval. So that means my confidence interval is between negative 1.0458 and negative 0.1142. Because both these numbers are less than 0, we can say that mu1 minus mu2 is also less than 0, which means that mu1 is less than mu2. Or reading it backwards, mu2 is greater than mu1. Recall from the last slide that 1 represents the red background people, and 2 represents those that had a blue background. So this confirms that having a blue background somehow enhances our creativity. Or maybe it's perhaps that for whatever reason, having a blue background does allow us to become more creative than having a red background. We are 98% confident the true difference in the mean creativity score between those who had a red background and those who had a blue background is between negative 1.0458 and negative 0.114. Well, this is all I have, and thank you for watching.